Welcome back. So Samuel will give his third lecture in his series. Over to you.
All right. So now let's go for the third, and then tomorrow the fourth talk I'll give about classical algebraic Chabauty. I will today mostly set up many tools we need to define the good objects, and then at the end tomorrow apply the method. So my talk was first titled Line Bundles, Abelian Varieties, and Log Functions. I'm not sure I'll have time to get to the third item, so I reduced the title here. First, I'll give some reminders on line bundles because we need them in a quite thorough way. If you know already much about them, you can tune out for, I guess, 10 to 5 minutes and come back afterwards. So let's start with x over k, proper smooth scheme over a field k. Okay, maybe not proper. Just smooth should be fine. I'll first give reminders of line bundles, as I said. So, and here, as opposed to Nitan's talk this morning, I thought it was slightly easier to talk about line bundles as geometric objects. Okay, so these are equivalents that say a word about this, but I'll really think about them as objects like this. So, as a definition, a line bundle L on X is another scheme L with projection from L to X. Often we write it like this. Okay, first thing. And then we want to say that the fibers are all lines, so K lines, right? So we want, that's why you could talk a line bundle as a special type of fiber bundle, but with lines as fibers. And we want to say that the fibers are not too weird when I locally change. The good way to say this is, and I have a cover, U alpha A open cover of X, such that when I look at pi minus 1 U alpha here, well, I won't say that this can be identified with U alpha times the affine line over K. This is pi. This is a projection to the first coordinate, so the obvious projection. And this will be pi alpha. With for every alpha beta and U alpha beta at the intersection, I want to say that I have chosen these kind of maps and they are compatible. Well, how to do it is that the formula is phi beta composed with phi alpha minus 1 of here x t should be. So this has to be x before, because this doesn't change the first coordinates. It's just go from xt to x. So I'm sure this is x. What's interesting is what happens on the second coordinate. So how you change it with the lines. And here it's phi alpha beta of x times t. And this belongs to the regular functions on x on U alpha beta. And star, because when you do this with beta alpha, you get the inverse. Okay, so you can just remember you have this locally, it looks like this. So locally, it really is a U, and you have U cross A1, okay, and you have lines like this. So locally, this is a part of X, this is a part of L. And because of this, this is multiplication, it's linear, it's non-zero. So you really can get a structure of vector space on each fiber, which is well defined, okay? And in particular, you also have a zero section. Zero section doesn't depend on whatever you choose in your cover. So each fiber is a vector space, a line, and you have a zero section that goes from X to L. By the way, zero section means morphism like this, that you get back here. And there, for every point of X, we get a 0 in Lx. Okay, by the way, I will often need this, so L star will be L minus the zero section. So I cut out this on every open. For those who know, that's because sometimes we want to think of it as a GM torsor. Okay. And afterwards, we have Lx, which I define as p minus 1 over x, or more as x star L. This is actually, if I'm over K, to be precise, it's not a K vector space, it's a Kx line. Okay. If you don't like it, think about the case where K is equal to K bar. Everything is algebraically closed, so that the lines are actually all K bar. Otherwise, you need to be a bit careful with the field definition here. All right, I give a few more definitions because afterwards I will not recall them often. So there is a notion of being isomorphic for line models here. Oh, by the way, if I choose another open cover, but you can refine the cover and get something like this, it's considered as the same L. Okay, because the object still exists. Here, we can say L is isomorphic to L prime if you have a isomorphism of schemes F here that commutes with the projection. Okay, and what's more, you also want this to satisfy the structure. You have this. So with Fx, which goes from Lx to L prime x linear. Okay, so the natural thing, you want to keep the structure of your line bundle. So here isomorphism. And of course, you can inverse it, then f minus 1 exists and it does what you imagine. All right, you can also define a tensor product of line bundles. Okay, I will not say much, just that it's made so that the fiber at L tensor L prime is the same thing as Lx tensor Lx prime. Okay, because of course the tensor product of lines is a line. Dimension is 1 times 1, so it stays 1, which is good news for us. Okay, and you also have L minus 1, which plays the roles of the inverse here, which is L minus 1 x. You can say this is a line and you take its dual. I think we did say dual here. All this can be rewritten completely just in terms of those. As Nathan said this morning, you can reinterpret many things about vector models just with the transition functions. This makes sense with transition functions if you want to be precise. So as an exercise, if you want to just convince yourself it works. And finally, you have the pullback. So for f from x prime to x of schemes over K here, you want to define something living above x prime and not above x. If you think about transition functions, you can just compose. So this is a function of u alpha beta. If you want to define what happens over x prime, well, you can cover by these kind of things and compose with f. And you get exactly what you want. And if you think about it, it's actually something living above x prime. You have x here. You have a natural projection right here. And here, you have a morphism, which I will call F tilde. Okay, such that F tilde from F star L at x prime goes to Lx and is an isomorphism here. So it's really what you can imagine. And if you think about the local covers here, means when you want to cover f minus 1 of u, well, just say, okay, I go to u and I look at what happens here. So it's copies of this. So there is not much difficulty here. And because this notion, so you have tensor product, inverse, pullback, many things you want, the first question you want to ask about line bundles is, okay, when I define something else, does it work well with these notions? So the general answer I can give in this talk is yes, but I will not have time in the next hour to give details. In the notes, they are here. So I'll just say that notion with line models is well behaved. Is well behaved. It's of course a bit vague. If it works well with tensor product -1 and pullback. Okay, meaning if it's a definition, you can extend for pullbacks, tensor products, as you imagine. And if it's a property, it's also compatible with this kind of operation. All right. So you might be wondering, even though I guess this morning you saw that vector bundles are important, line bundles also. But I want to convince you not only that they are useful, but they can define really very powerful stuff. So the basic learning we can do for this is over Q. So over Q, you can define for line bundle, so L over X defined over Q. You can often define a height over points of X here as a sum like this. So this is all the places of Q, so all the primes and infinity, or I'll keep it in place. And you can define something like this. And I will explain notation right now. Here. So this will be a norm on Lx here of QV. So I look at the QV points above X of L, and I define a norm on it. I choose a norm, and I choose it well. I don't make any details here, but I choose a norm here for every V. So, and then I took the log of this norm. And what is U? I should mention here. U is L above X. L of Q above X. All right. It might look a bit weird, but it's exactly what you usually do with heights, just rewritten differently and very powerful. First, maybe as a sanity check, why does it, is it well defined? Because I choose a U? Well, because these norms are so that when you multiply by a scalar, it does what you imagine. So when you change L of Q here above X non-zero, it amounts to multiplying by a rational number. And because of the product formula, it will not change the total value here. Okay? So it means when you put a norm on each of those, on each X, in a nice way, and then you do this, it's well defined first. And then, and also it retrieves many notions you can imagine about heights. As an exercise, for example, you can retrieve the Weil height with P1, Z, and Q, I think enough, and O of 1. Yeah. You can define notions like this so that you can exactly get the Weil height of a number with P1 here. So this is a nice process. It's very powerful. You can also, that's basically also the fact that you don't directly define something over X, but for sections. You can, for example, find it also in the definition of Falting's height, another height that's very interesting. So the idea of doing this is not so difficult, but I'm just easing you into what we'll try to do. I will imitate this with values in QP. That's the goal. No, it's actually here, X is a point of X, okay? So I have a X is here, I take U here. So the global place here is, no, it's not like this around, it's like this. L is this, okay? This would be X. I take U just in the fiber Lx. I take any rational element in the fiber above, and then it doesn't depend on this choice, as long as it's non-zero. Okay, and just it's a product formula. Okay, this was very natural because it makes sense in this case to put a metric on this. So a norm is a metric, of course. To put a norm on every fiber here, try to put it together and measure. Okay, we take the log so that we have nice properties, for example, for everything we want as a sum or something like this. But here, the idea is you start from there, you get a real number here with a norm, and then you apply the log. All right. So you go from something variadic to norm to R and then log. Well, of course, we cannot do that with QP. We need to sort of put directly something from QP, from whatever happens to QV to QP. Okay, we cannot afford to go through R because going from R to QP is, well, doesn't give good results, right? So we'll have HL of X of this form here. So this will be from L star of Q V to QP here with the same convention. We will define functions like this, okay, and we will try to define them very well so that they satisfy very nice properties. Again, if you think about this, one very special example is a neontate height that actually Jan mentioned. The neontate height, I think you're convinced now that it's powerful because that's what allows to prove whether Heegner points are torsion or not. And so you can use L functions and L ranks to determine this. All right. Well, neontate height, you can also write it like this. It's part of the process. And it has a very special property that it defines a quadratic form with values in R. We'll try to do the same, but with values in QP here. So of course, I'll need to explain a bit what this means, but we'll try to do very special choices to ensure this. Okay. First, also, before I dive in the more details, as opposed to what happens here, where you want to make a lot of good choices, you have norms and p-adic norms that happen, there are a lot of them. Here, you want to go from something v-adic to something p-adic. There are not that many natural ways of doing this. So first off, I should do it immediately. HL infinity will be 0. Not talk about this in our case. I should have said geometric integral maybe here. Yeah, just to be sure. But I only have one connected component, otherwise some stupid things can happen. Here. This will be 0, so I'll never talk about it. The first ones I talk about are the HLQ, with Q different from P, okay? It has to go from something Q-adic to something P-adic in a natural way. And again, if I want to be a bit algebraic, I will not have many choices, so it will be quite simple to do. There will be a natural way to figuring out what should be here. So the only term that's interesting, or actually difficult, is HLP. Okay? And as I said before, here I take the norm, then the log. Here, there is a natural version of the log, but still, I need to sort of incorporate this. And this is what will play the role of log function over L star Q. Okay? So I need to be able to create those and make them have a good behavior. All right. So that will be the goal of the next two talks, and then to use them. So first, I go back to the line models and give a bit more details about the theory. So, oh yeah, I have one more board. Again, some reminders, but it might be useful just to make it clear. First, there is a group formed by line bundles with tensor products here, and I cautioned by the isomorphism relation. It works, and it defines a group, and it's called a Picard group. Now, maybe it's a moment to mention, if you already know some other definition of Picard group, maybe you might be confused, but here, line bundles are the same as invertible sheaves. Which are the same for X smooth, sorry, here, in the smooth case, as OX of D, so D divisor. Okay, and so you get back to the group of divisor. Up to, and the equivalence here means rational equivalence here. Okay, in the case here, and in the case of curves, you do get the divisor of points divided by the divisors of functions. Okay, so I'm mostly on this side for the talks, but if you want to imagine what's going on, you can always translate in terms of those. All right, small notation. I want to define properly what is a restriction. So I will often define line bundles in two directions. So L living in something, so above X times Y, okay? I will often consider slices. So this would be, for example, this is constant in Y, so this will be something like here. Right, and another slice in the other direction. Here. So this is part of here, but of course here you can think of L as three-dimensional. So there is something living in L above this slice, and above this slice. So L should be something like this. And here something like this. This should be, say, X times Y. Of course, here, geometrically, it's the same thing as Y. Here, it's the same thing as X. So what I'm just saying is that when I take something like this, I can slice, and each slice gives me a line bundle over either X or Y. I will consider this. That's exactly what I do. So for L above X times Y, Y satisfying the same properties here. For X in X of K bar, I define by notation X times Y being the pullback of L by IX, where IX goes from, actually, you want to say it goes from X to X times, Y to X times Y, by saying Y is sent to XY, right? This is not always well defined because little x might not be defined over K. So we need to extend slightly over K of X. Otherwise, it's fine. And similarly, for when you slice the other way. All right. I forgot to just make one small definition. Maybe you can ask some people, what do you think should deserve to be called the trivial line bundle? Before I say more things. Yeah, X cross A1. Trivial thing is really this drawing over the whole X. You have trivial transition functions with 1. So this will be the trivial line bundle, just the product, okay? And this, of course, if I think about it, it will be the neutral element here, okay? Now, something I maybe did not want to talk about too much, but I think I'll end up doing it. There is a marvelous principle that's very visible about line bundles. It's the seesaw principle, which says the following thing. Take L like this above X times Y. Imagine that I slice for all slices like this, all the red slices, I slice everywhere, and I get the trivial bundle up to isomorphism, okay? I get something trivial like here. This is not exactly enough to ensure that L is trivial itself, you have counter examples. But if you have one more slice in the other direction where L is trivial, then L is trivial globally. Okay, that's at least on a proper variety. But in all situations, I use it afterwards. It's what happens. It's very useful to prove that some line bundles are trivial with this kind of spaces, and I'll use it often. All right, so now let's go for another definition, which is, I'll not say much about it, but it's a slightly stronger equivalence relation than the isomorphism relation, which is called the algebraic equivalence. Right? So, let me check, yes. I take two line bundles on X. I write them as algebraically equivalent. So equivalent if I can find another variety T, it's also smooth and geometrically integral, such that I can find T so that one slice of T, there is another also line model and L over X times T, okay, such that one slice of L gives me L1 and one slice of L gives me L2, basically. And I can also rewrite this as L1 tensor L2 minus 1 is isomorphic to L sliced at T1 tensor L sliced at T2 minus 1. This is a more general relation of equivalence. You can check it works. I have, again, details in the notes. And the pk 0 of X is exactly the set of line bundles on X with tensor up to this equivalence. I think, and because you can see quite easily that being isomorphic means being rationally equivalent, you can say that because of this, it's inside the pk group X. Here, as an exercise, you can do the case of curves. For the case of curves, let's imagine over a K algebraically closed, it's quite easy to find that this is exactly the set of divisors of degree 0. Okay. For example, take just 2 points A minus B. You have to find something like this, a T doing the job, and well, it's a quite simple exercise. I suggest you try it, but it's not very difficult. So in the case of curve, we retrieve exactly what you know about X0 or div0 here. All right, now I can define this. At least good candidates and what should happen. All right. Okay. A Q valuation on L defined over XQP. Okay, I take something defined over QP and I want a Q valuation for a QQ here. I try to keep the Q here. I might forget at some point, but to say it's different from P, it will be Q all the time. The function VL from all points except the 0 points of the bundle. So Q bar to Q here, whence name Q valuation, such that what I imagine should be the role played by the log here. So if I think of it for a bit, it's any non-zero lambda, any U here in L star Q bar. Okay, I should have VL of lambda u is equal to, well, the valuation on QP bar starts, so I can call it the order. This is QQ again. Order Q of lambda plus VL of u. Okay, so think about what happens here. It looks like the same thing. That's something I want to define. And then I can say right now that it works if I define something like this on L, it can be defined on tensor products, on pullbacks, etc. This is well behaved as a notion. You can be pretty creative with this. It's really easy to define it on other bundles. And another remark that's important is you can define it also easily if this can be made integral. So if X over ZP is a smooth model, let's say proper here. Model of X, okay, and L, main bundle extending L on X, okay. So instead of having just a generic fiber, you have things over ZP. Well, there is a very natural way of thinking about this, and because of the following, if you restrict L to UI, to some UI here, it's the same thing as UI times, this time not A1 QP, but A1 ZP. All right, and this can be sent inside what is usually L to UI, which would be UI QP here times A1 QP. In other words, you have a natural way of thinking about points as integral in the fiber here. Inside every fiber, there is an integral structure. And when you have integral structure, you have pretty naturally a candidate for the valuation. You don't say that a generator should be a valuation 0. Yes. Oh yes, again, sorry. Yeah, this is it's Q everywhere. Yes. I should have written R and replaced everything by QP afterwards. Would have been clearer. Yeah, thanks. So here, A1 ZP, A1 QP gives natural integral structure on the fibers. So VL of U is equal to 0 when U above X generates this structure. A bit vague here, but it's a quick exercise to define this. Okay, so you make this choice. When you have this integral structure, you just decide that the valuation of something that's generating structure is 0. It's a big that when the valuation is 1, which generates ZP, is 0. Is the usual valuation. Same thing. And it doesn't change when you change how you represent the fibers, because for such a line bundle over this space, which I didn't give details about, the transition functions have to have value invertible as well. So it doesn't change the valuation that you'll end up with. It doesn't depend on your choices of trivializations, etc. It's well defined, and well, it deserves a name, so it's called an integral model valuation. Okay, so this means when we have a model, we have almost for free something like this. One last general definition about line bundles. You have, I guess, already noticed that there is always an ambiguity with the line bundles, because except the 0 section, well, everything else is just a line with no clear candidate for a basis. All right, no canonical one. Well, sometimes we really need one. So a rigidified line bundle L R with R in L star of, let's say K, here, fixed. Okay, so I will fix one element in one fiber, non-zero, and I will say this is my rigidification. Difficult to say. Should find a shortcut for this. Okay, so this is one choice here, and when you choose this, well, it makes a lot of things easier. For example, when you have an isomorphism of line models, you can multiply by many things and still get an isomorphism. If you want to send R to R prime above the same point, you have only one choice now. So it makes things much more rigid, which is the reason for the name here. And for Abelian variety, we always choose R above 0, okay? Because there is a natural candidate for a point, which is 0.0. We choose something above the fiber at the fiber of 0. All right. This is also well behaved. When we fixed a rigidification for L, it can extend to for tensor product, for pullbacks, etc. Again, check it out. It's not very difficult. All right, now I can state the theorem. More room to say that basically we have done all the work here in one swoop. So let's state it. I'm just quoting the theorem because it's slightly harder than it looks, and I'll explain why. So there exists a unique rule which to any x as above, QQ, any LR rigidified line bundle on X associates Q valuation VLR, okay, which that's one. Maybe I should say an obvious thing. If you have defined a rigidification, what do you want for the value of R to be? The preferred choice of elements. What do you want to be? It should be. If you associate to any LR evaluation, what you canonically want it to be? Valuation here, as I have the ID here, by the way, to be 0. That's just the base point 0. All right. The other one is that V for the trivial bundle OX and trivial rigidification here. So you can associate, so it's with X and T. This will exactly be evaluated the order quadratic of T. Okay, so just every fiber is the same. It's a A1, it's a Q star, so it works. Bar star actually. 3. I said once you have one, you can define a lot of other ones. And I'm saying the process here works for this. Saying well behaved. Here again, you got in the notes. 4. You want it to be topologically non-stupid. So let's say it has to be locally constant on L star F QQ bar. All right. And with bounded denominator on L star F. Again, just to have something that's not too weird. Okay, the remark is that basically, if I know I have an integral model, there is a very natural choice of evaluation. And that's exactly the difficulty. When I have this, I'm fine. But why the theorem is pretty strong is that it also works for more general situations where you don't even have good integral models, etc. So it's quite general. pretty neat. All right, so this sorts out just the case of all the parts of the height except the p-adic part. Unfortunately, I have a lot of background to explain before we get to the log function at p. And I thought it would be, well, also to make you understand a bit of what's going on with abelian varieties, I will give a lot more information on what happens for those on abelian varieties. And it's basically, they have a lot of interesting properties. Yeah, exactly, yes. Locally constant, exactly what it means. So actually, it will be very, very constant in many cases. Yes, that's true. Here actually, yes, here actually it will be a function here to Q. So by topological arguments, yes, it has actually only finitely many possible values. And I should say it right now, in our cases, it will be under nice hypothesis. If I have a good reduction, it will be actually it will be constant in this case. And even 0 if I have rigidified property. Oh no, when I mean constant means constant on a good choice of yeah. Yeah. So it will not be difficult here. Not posing this really at the end, I'm just writing for some formalism. At the end, think of it as all these terms will bring something like either 0 or a finitely many possible values in a contribution to the height. So it's not too difficult. Now I want to explain a bit more about abelian varieties, as I said. So first, we mentioned it before, but now I really want to insist on its exact properties. Okay, so I fix A over K abelian variety with dimension G. Okay, you've seen it before, but it has a dual. And I'll explain what it means to have a dual. So there is a unique dual abelian variety. A dual and something called the Poincaré bundle P on A times A dual here. So that is such that well, first one is what characterizes a bit more precisely A dual is that for all extension of fields K over K, if I want to look at the line bundles equivalent to 0 over K, okay, this might seem like a very big space and you don't really know what happens. Actually, it's exactly parameterized by the set of K points of the dual. By the way, if you think about it, we talked about moduli spaces in very specific context. This also is something that looks like a moduli space. Moduli space for device moduli space or line bundles equivalent to 0 here, right? And this is canonical. I will often make the identification without mentioning it. So this is for a dual. And what does P do, the line bundle? Well, there is a very natural process to define it. For every point of the dual, which you now know come from line bundles here, well, I can restrict P to A times this, okay? So this slice is line bundle on A, but this also can be considered as line bundle on A. So I'm saying this is the same thing. In P0 of A of C, okay? I suggest you think a bit about this statement because for me, I thought it weird the first time. Natural when you really think about this, but it really is an equality between line bundles because this defines a line bundle. And P restricted to the slice at 0 on the other side is trivial. Okay, and by the seesaw principle, I define P on every slice like this and on one slice like this. So actually it's unique because of this. And given how it's defined, we'll see that many properties can be just obtained by slicing in those both directions and see what happens. All right. Now I can explain what I think, in my opinion, might be the most important statements about line bundles and Newman varieties. Maybe I will have some protest about this for some people with other strong opinions, but that's really my favorite one. Okay. So for X inside A of K bar, the X is a translation by A. I can translate by adding X to every point, right? And now what can I do with this? Well, I can start with a line bundle here. And I can send the line bundle to, well, this thing. Every X on A, I associate the translates of L by X. But then I actually want to land in something that's sort of degree 0. And what means degree 0 here? I take L minus 1. So look at the difference between L and its translate, basically. How is it different? Tx L by L. And this lands from A of K bar here. And this lands inside the PKR of A K bar. But actually, this will be equivalent to 0. Actually, it's basically it's almost trivial given the definition I gave here. If you think about it, how I defined equivalence here, it's almost obvious that this lands automatically in peak 0. All right. So this is, I call this phi A L. I call the big one phi A. And now I have many things to say about this. The first one is that this map from A of K bar to peak 0 of A K bar, this is the same as A dual of K bar, right? So I get a map from these points to these points. This is actually a morphism of abelian varieties. Between A and its dual. All right. And the map from L to phi AL is linear. This is, it's obvious. Oh yeah, maybe a keyword for this, but it works with addition and other operations. I never know which is which and which to use, but I can tell you it's contained in the union of two statements, theorem of the square and theorem of the cube of abelian varieties. Look it up, and then after these very big theorems, you can get this pretty easily, that it's homomorphism. In particular, image of the sum is sum of the images. Here, and second thing, we actually know when this is trivial. So when phi AL is 0, so the kernel of phi A is exactly our group 0 of A bar. So we know all those would give nothing and the other ones will give something. Why is it useful? I just dropped this now here. It will come back right at the end of the talks. It's useful to get a bit of a feeling about this space. The Néron-Sévère group I defined in first lecture, which is here, the quotient of these two groups. Well, this injects because of this in the morphisms between A and A dual. And I realized I didn't say one other property of the dual. Yeah, it's like as dimension G here. It's a property as dimension G. So I'm looking here at a morphism between something with dimension G and something else with dimension G, abelian variety. Think about complex tori now. This is C power G quotient by lambda. C power G cosine by lambda prime. The G-dimensional version of what Professor Gate said, I think first lecture, tell you that this has to have a small dimension. So then module of rank G square, and also 3 by the way. At most G square. As an exercise. So you can actually bound at least to the C happens here. All right. Now another important statement. Here, well, we want to make use of other maps on abelian varieties because we do have canonical maps. We have multiplication by n, and we have the sum difference, and for example, from A times A to A. Okay. Well, I'll say a lot about those right now. L on A is symmetric if, when I look at -1 star L, it's isomorphic L, and anti-symmetric if 1 star L is isomorphic to L minus 1. Well, makes sense as a definition here. And then I can give some properties of those. So define this map. So the sum here, the difference, and the projections. Well, what I can prove and what's actually an exercise with the seesaw principle. Not very difficult. If L is symmetric, S star L times D star L is actually the same thing as P1 star L square times P2 star L square. And this has a quite natural consequence. Again, check it out. So for all n in n star, if I take n star L in the case symmetric again, this is the same thing as putting L to the power n squared. And this is our first hint of something quadratic happening. There is something quadratic here going on in the case of symmetric line bundles. So if L anti-symmetric, I should say right now, unfortunately, or fortunately, I don't know, it looks like something linear. I get something. Here. So I should maybe emphasize this because I didn't write it just for fun. What I pretend is that once we have a good machine to build heights from, let's say, symmetric line bundles, that's functorial enough. Because of this, it will be quadratic. Just because of this, actually. And I'll explain next. So tomorrow I'll give the details, but think about it. This is exactly what gives you the quadratic behavior of the heights you'll get at the end. But it's just a matter of what happens to the line bundles. And maybe, yeah. Here, maybe as an exercise, if you want to really say something that a function is quadratic, you need to think a bit to make sense of it. So, as an example, take this. Take F and you associate F star L, of course, for another abelian variety A prime. think even something general works. Let's say a prime. Maybe in writing. You want to say that this is quadratic. Okay. Think about what it means. I will not tell you what it means, but we can really make sense of it. Quadratic function. All right. Okay. So finally, one last property that tells you, because for now I have done some advertisement for line bundles over A in general, not so much for the Poincaré bundle. Well, maybe you've guessed it, but these properties are universal properties. They are built as by universal properties, which make them very canonical. But even more than this, we have this result, which I like because it also tells us something. If L is symmetric, I have this morphism, so PAL, which goes from A to A times A dual. Okay, I said phi AL goes from A to A times A dual here. So A times A dual. Here, I add the identity. So it goes right where lives the Poincaré bundle. Okay. The question is, what's the relationship with L? Well, it's very simple. It's the square of L as morphic to this. Well, I should say also P is symmetric. Maybe that's something you want to say before. This of course doesn't depend here. So this is already symmetric on A times A dual, but you can retrieve L square by this. Even better news, because now you don't really you don't really want to define things for every line bundle L symmetric. If you can do something that's good enough for P, because of this on the pullback, you have a hope of having defined it for every L. Right? So that's also one thing that will appear tomorrow. Okay. Now it's appeared a lot of times already, but I will need to give some more basics on this. And in what we'll do, we'll rely a lot on what happens for the Durham cohomology. So I prefer to just give you a lot of results that helps understanding what's going on with the cohomology. I should say, I'm not an expert myself at all. Okay, so I just picked the results that I thought would help to have an idea of how to tackle these kind of things. I don't think recalling the definition is useful because it's not very enlightening, but Nathan gave it in its talk with the hypercohomology groups, etc. I'll just recall you to have in mind that there is a sequence of a complex of sheaves with differentials, okay? And you can define it for a polymorphic, or regular, for algebraic function and form, but also it extends to locally analytic functions and forms, etc. I will use D all the time. So X of a K smooth. So first, if X is affine, well, it's what we imagine. So the Durham cohomology of X is exactly the nth cohomology group of the sections here. I think that's how I should define it. So you do get closed forms over exact forms, etc. So as the usual Durham cohomology over R. Second, that's the first good news, because I think for me it's not that helpful because we don't have often affine objects for us. Or any K over K field extension. Well, it behaves nicely because it's a vector space of a K. And when you look at the extension xk prime over K prime, so basically base change X, it's the same thing as, I should say characteristic 0 here. You sure? Here, it's the same thing as extending this space. So if you want to understand it, a bit of it, and by, for example, for all our cases, you're looking at fields that can be embedded in C, you can do everything over C and then at least deduce something like the dimension, etc. So you can think of it over C, and that's precisely the goal of the next item we're going to talk about. Oh, I need some room for this. Item C will be a lot of things here. So if K is equal to C, well, the idea is we know what is this cohomology. And I assume here X proper. Even projected. Okay, if K is equal to C and X projective, then X of C, C points, is a complex Kählerian variety. And a lot of things happen. And first, I'll explain. This is isomorphic to the singular cohomology with coefficients in C, which is in turn isomorphic to, so I should state this, the Ram cohomology of X of C as a complex variety. And this can be decomposed. And this is the Hodge decomposition. Here, on some partial spaces here, which are much more explicit. I'll just say right now what they are. Here. So this is infinity harmonic forms of type PQ. I think I asked them to be exact, yes, and divided by exact one. Okay, so this is much more explicit. I'll give for n is equal to 1 the consequence. And this is very simple. Here, I can split H1 de Ram of X of C, X over C, into two parts. First one is omega 1 X of C plus omega X, okay, omega 1 X here, 1 X of C bar here. Correct, yes. Okay, so we have on one hand the holomorphic forms, on the other hand the entire holomorphic forms. But this gets easier. And this is very important, called Hodge decomposition. It means two things. It means first we have a natural space of forms, which we actually, by the way, can bring back from X over K here. And we have some supplementary here that's given by complex conjugation. So this is very convenient. It helps us do compute very nicely cohomology. We split and we just use this sort of decompositions all the time. Unfortunately, we don't have this over QP, of course. Well, we have natural definition of forms. We have nothing sort of definition or a conjugate. Many things I'll do afterwards that might seem a bit weird. It's because we try to imitate this kind of phenomenon. We try to imitate this fact that we can find a supplementary here. So I will get back to a general field K, just to say at least what is sort of canonically defined over K. And we have this. So here I just in the case of curves here is a curve of genus G. So again, smooth projective here. Well, now I have many things, but it's pretty easy to figure out the Ram cohomology. It's K, and it's the same thing for H. What did I write? H2. No, I didn't write H2. Sorry, let me just write the flip ones. Yeah. x, okay, is equal to k as well, and it's also isomorphic to, we want to have it, h1x omega 1, and also h0x ox. So all this is k. The interesting one is the h1, and it's been already shown in previous talks. I have a canonical sequence here, exact sequence here, from this space to h0 x again x equal 0. This is dimension g. This is dimension g. Okay, so as you can see, here also we have natural injection of one forms inside this space. So sort of half of the space is given by this, and I know it. The problem is the other half. It doesn't split for a general K. So I do not have a good candidate for this. But there is a sort of other option. I have also an explicit description for this. So it's the space of second kind differentials. Represented by exact ones. I recall just by saying it, differential of the second kind is meromorphic differential, so larger than this, but with only 0 residues everywhere. So where there are poles, the poles do not bring any residue. Okay, and we can prove that it's actually the same thing. And again, of course, it commutes with the, this identification commutes with the natural injection. Okay, so that's how we can see what happens for the RAM cohomology for curves. All right, I haven't talked about abelian varieties. I'll just say maybe also holds for abelian varieties. It's also a dimension 2G, etc., etc. All right. Finally, I'll explain here something called the Chern class. And again, maybe taking it as a black box at first, but over C, it's really natural definition. For a complex scalar variety, you can define it quite naturally. And even better for abelian varieties. Here, I have a natural map from peak 0 of x to the second Durham cohomology of x over k. Here, by cohomological arguments. And which to L, it's C1 of L, call it Chern class. Here. Just maybe take it for now as a black box. It's not very, I can just maybe just I can convince you that we can do at least go from Picard group to H1 of x omega 1. This one is not too difficult. If I have phi alpha beta as transition functions on the line bundle, I define d phi alpha beta over phi alpha beta. It's well defined because the transition functions are non-zero everywhere, so I can define this, and this defines a cycle of one forms over x. Okay, so I can go from there to there. That's pretty natural. And now, cohomologically, going from there to there, it's a bit more involved. But that's what it sort of registers. All right, I've almost finished setting up all this. So we'll get back to good old functions. Well, good old, I should not say, but to functions that maybe are a bit more concrete. So, for now, in terms of functions, we have many types, especially because we saw a bit of rigid analytic geometry today. But basically, you start with the algebraic functions, okay, on a scheme, so regular functions, etc. You want to extend, especially over QP. You can extend, and when you extend, for example, with rigid analytic geometry, you extend some functions, but it's still not a lot, okay? And at the other extreme, the bare minimum that you want is that locally, your functions should be analytic, okay? Because, well, if you don't know how to do power series, you don't know how to do many things here. That's slightly too general for us at first as a general space. So here, let's take, I'll just give it in this case, so X over QP with a smooth model here of a ZP. And actually it's useful in much more generality, but I just give this here to give you the idea. In the notes, I think I'm slightly more general. O log of X is the set of function over XQP bar to QP bar, and I should do here. Oh, let's go now. Actually, QP bar, sorry. But on each, for each X in X of FP bar, F is analytic on the residue disk. Okay, so you don't allow to choose the expansions in a whatever way. You really want on residue disk to be analytic. So on this disk, really a power series. Okay, so it's a bit more restrictive. And now, and you can do the same for forms, etc. So I'll not explain that you can do the same for any forms. Defined by power series. So you want things to be nicely shaped on residue disk. All right, and once you have this, I'll explain what kind of functions we'll use to play our game to find the logarithm functions. It's these ones. So we have Fourn, and I think more generally it's called Vologodsky. But for smooth cases, it's the same as Kalman functions. So this is a regular ring of over X, okay? This is at the other end, it's O log. So all the ones that reduce, that are all the ones who are locally like this. In the middle, we'll define something called OV of X with some more properties, and I'll explain afterwards some properties. Okay, I will not define completely, of course, but I will just say what's supposed to happen. To give a summary, I'll just wait for the 2 minutes. I give an exact sequence, which gives you exactly what's supposed to do. Okay. Maybe also I should announce immediately that on GM, log of Z, okay, on GM log of Z, so it's a primitive of dz over Z, belongs to OV of GM. Okay, good news, I have the logarithm that the Gould one I defined. That's already something. And now, what they are really made for, these functions, is the following at least. It's the sequence. Again, oh, here I need to take, yeah, X geometrically integral, I guess. Maybe proper here. Yeah. It's fine. So I have constants there. I can derivate here, omega 1 v of X. And then I derivate omega 2 v of X. And this needs to be exact. And basically, that's really what you want. What happens? You start with a good old one form here. Assuming it's closed, so d of omega is 0. You're here. You want to integrate it. Okay, well, you cannot do it usually, but with this, you can integrate it and get a function here. All right, so now you get functions. You have more functions. You can multiply those functions with previous one forms. So you're in a space that's bigger than omega 1 here. But then again, assume that you compute again and it's closed. You want to primitive it. You want to, this allows you because you're still in omega 1v, so you go back here and you primitive. And again and again. So this exact sequence tells you basically that you can do iterative integration. Especially in the case of dimension 1, because in dimension 1, every form here is closed. So you can really do this without thinking too much about is it closed, is it not. Okay, so this is basically the smallest space where you can do that. Integrate and iterate every time. And as you can imagine, you start with the primitives of omega 1x, and then you get some more functions. You add these functions, and then you get some more, and you primitive again. And so it's sort of a limit process at the end. Sorry? Oh yeah, here, if you start with an ordinary one form here, this allows you to integrate it and find a primitive here. Okay, so you have many primitives now. You can add them to the function, but also to the forms. You multiply these to the forms. And now, well, you have new forms you might want to integrate. Then this allows you, because it's closed, to go back here and find another primitive. And you can go on and on. And so it's built by sort of steps here. In particular, what I just said, the first example here should be this. So first time iterated integrals. Okay, so this will be built with omega 1 and with all primitives of forms of omega 1 I can find. Right, so this is, of course, included in this. All right. Now, because this is sort of just a definition, in some sense, as I gave you, of course, it's a whole process to construct it. But we'll need a lot of this, which might seem less intuitive for the moment, but still, I should recall you here. In this situation, you can split into two parts, and it's also because you have two differential operators. You have D splits into delta and delta bar. You can derive for Z or for Z bar, and this is also what's originating this split. Well, you cannot do this in general for over QP. There is no complex conjugation, but we try to imitate it. And there is the following delta bar operator. So again, thinking about the complex case, that does this. It goes from this space to this space. And if you don't understand why you go there, maybe you should here. We want to go from one form to two forms, but from omega 1, we want to go from omega 1 actually to omega 1, 1, omega 1, 2, omega 2, 1, but we don't have a definition for those. So the sort of substitute we got is to look at things inside this space. It's not much better, but at least I can say that here it's defined this way. So this should be what? This should be the really old one forms. So omega 1x. This should be primitives of one forms here, of one forms here, and x. And it's defined in this way. It's that you get the sum of omega I here, and you go the class of the fi. Okay, so there is something weird here. I'll explain immediately. Maybe you're not used to look at H1 de RAM, look at a D something, and don't think it's trivial, right? You have derivated something and you expect it's non-trivial. That's normal because dfi, so fi is not a regular function. So it has no reason to be d of a regular function here. So in general, it's non-zero. So it makes sense to talk about it. All right. And so here, and we have an exact sequence, which is also why it's interesting. So this is contained into this space here. And you have an exact sequence with only the one forms get cancelled. Here. And apparently if X is affine, this is even surjective. It really gets everything you want. Right. How much time do I have left? I don't have a 10 minutes. Okay. Oh, okay. So I have 10 minutes. So I can finally define what we like as a log function, but I will not have any sort of time for the properties, but still I can say what we hope for. Again, this theory is well, sort of meant to imitate the complex case with many difficulties. And the fact that we iterate integration should not surprise you by now. That's something we can do. Being a bit careful. So I can actually define line bundles. Log functions. L line bundle on say XQP. The QP line bundle. And here P is really P, it's not Q, it's really P. And there I'm looking for periodic things. A log function on L is a function log subscript L, playing the role of the height I want, so L star of QP bar to QP bar, such that, well, the obvious objective is to allow for a product formula and to have a right behavior with respect to linearity. So this is exactly what I'm writing now. For all lambda in QP bar, for all U inside star QP bar, I should have that log L of lambda U is equal to log of lambda plus log L of U. Where you should remember, I define logarithm on QP bar star to QP bar. So maybe I just say QP, but it's the same. I normalize by log of P is equal to 0. Okay, so this is well defined as a function in QP bar star. So P linear, that's fine. Second condition is I want D log L. So this makes sense inside things on L star, and I didn't say which kind of function is this, but now you know. It's supposed to be a one-time iterated function over L star. So in other words, I'm supposed to be able to build log L by integrating function on L star. I don't want it to be too complicated. I want it to have a one-time integration here. So sorry, you say I want log L to be a primitive of something obtained after maybe one-time integration. So if you just add 1 plus 1, which I just failed right now, it's 2. 2 times integration should give you a definition for log L. And we'll see, I hope, explicit formulas tomorrow. What does it look like? Here. Maybe here, I should say, we also want LR is rigidified. Again, we want R to base our value on R. Log L of R is equal to 0. Okay, and of course, the definition we want for the trivial bundle, so X, and the one trivial rigidification should be here of x u log of u. These are natural definitions we want to have. And I should say right now that these notions are well behaved again. Meaning, just by formal computation, you can check that for two linear models L and N prime, the tensor product, and you have log functions for each one, you can define a log function for the product. You can do this for inverse, and you can do this for the pullback. Also because I didn't say it, of course, but no, I forgot the functoriality here. Did I write it? Did I just? Oh yeah, sorry, I forgot about it. Obviously, there should have, you should be able to pull back these functions. Okay. So I want to say here, if you pull back, you can pull back these forms, and it's also all commutes, etc. So once you can do this, you can check that if you pull back something to x prime, this is still satisfied and satisfied. So you can get pullbacks of log functions. Okay, in a few minutes, I have here. I have 2 or 3 minutes. Or, 5. Okay, so I can just say 2 more words of vocabulary. Because now, how should I say this? For now, this and this is 2 conditions, but it's already too many. It's already we still have a lot of choices actually. I have too many choices for now. There is no good way to build log function like this. Okay, we'll add 2 more things. First one. That's function is for L symmetric at least. Well, symmetric, we'll say that log L is good if minus star L endowed with log, so minus star log L is isometric to L log L. Okay, I didn't find isometric, but it's pretty transparent. You have line bundles, you have which can be isomorphic, and you have metrics sort of obtained by log L, and you can go between fibers or isomorphisms, and you want this to be to be what you imagine between fibers. All right, work it out again. It's say well behaved because also you can define isometries in a natural way. What I'm saying here is that you have L log L, you can pull back log function of a -1 star log L, and this defines canonically log function here, but you also have an isomorphism between this and this. I should say you should also rigidify here LR. When you rigidify, this also has rigidification, so it also fixes your value of log L and -1 star log L, and you want this to be an isometry. So it's a sort of, it means that when you, basically what it means is that when you take log L of minus something, it will be what you imagine. Not that interesting, but still. Second one is much more interesting. Log L is, should I say, is it canonical? Check something. Thanks to writer is canonical, but I want to be sure. Oh, is it symmetric? Okay, symmetric. Okay, sorry, canonical will be later. This is symmetric. If you remember properly, I had this for a symmetric line model. Or some difference and projections. So this leaves This lives on A times A for a line bundle, so for A here. Oh yeah, over A abelian variety. Here we cannot define, of course, over something else. This is an isomorphism. It's sufficient to rigidify L for R, and I have rigidifications here and here. So I can have one unique isomorphism well defined. Okay. And I'm saying log L is symmetric. If I put the canonical things on every term here, I should get an isometry here. And this is exactly what will make you, I cannot state it right now, but that's basically the idea, that log L of a sum plus log L of a difference should be equal to twice log L of something plus log L of something. And this is one of the formulas that characterize being quadratic. That's what we want to end up with. Fortunately, and I think that will be a good time to stop, even asking for these conditions is not enough for one unique thing. There is something hidden there, some sort of undetermination, and that's called the curvature form. And I will define it tomorrow and say once we have fixed this, now we'll have a unique way to define a log function that's doing everything we want, and then put it together, and we'll have a height functions. And once we have a height function, you'll see it be pretty quick. Okay, sorry, it was a bit of a setup talk, but thank you for your attention.
Any questions or comments? Just very quickly. Will you construct this OV and omega 1V, or like could you just say how to like enlarge this? So X,
I said if you have a good theory of integration, that's what you do. Yeah, I should make clear. So with the paper I'm basing my things on talks about Vologodsky functions because they want to do things even over non-smooth varieties, etc. So they need to develop the theory in a very general setup. From what they say, even it's not clear, there are some incentives, but basically it's the same thing as Coleman functions in a smooth context where you have a smooth reduction, etc. So then basically they just define. It's called Vologodsky functions, which they do, and that's basically what it does. It extends the notion of regular functions with the connections and develop connections, and with connections you can define more functions because you integrate. And once you integrate, you can do this. And the fact that what corresponds to iterated integrals, basically, it's unipotent octogonal. So you do one by one, and you get, at the end, you get, when you take all possible things, you get this. Yeah. And Neta, I think, showed a bit more of what's under the hood. I showed just so, well, there are these, and that we try to compute with it.
Any other questions or comments? Okay, if not, let's thank our speaker again.